Welcome back, everybody. We're diving deep today into a paper that's, well, it's foundational, really, even if the title's kind of dry. A note on two problems in connection with graphs, it's called.
Yeah, you're right. Not the most grabby title, maybe. But trust me, this 1959 paper by Edgar W. Dijkstra, it's anything but boring. It's like the seed that grew into so many algorithms we use every day.
Okay, so before we get lost in the woods here, let's set the scene. Graphs, in this context, we're not talking high school algebra.
Right.
More like networks, relationships between things. So
Right.
think maps, the internet, even like social connections. And Dijkstra, he tackles two classic problems in this world.
The first one is finding what we call a minimum spanning tree. Imagine you're laying cable to connect a bunch of houses, right? And you want to use the least amount of wire possible. That's what this algorithm figures out, and it does it efficiently.
So it's like being super thrifty with your cable, but is there a catch? I mean, picking the shortest connection every time seems almost too simple.
That's what's brilliant about it. It's what we call a greedy algorithm. Always goes for the immediate best option. Doesn't always work out long term. Think about packing a suitcase haphazardly. You might end up with wasted space. But Dijkstra, he proved that this greedy approach, it does lead to the absolute shortest tree overall.
Wait, hold on. Back in 1959, he was already doing mathematical proofs for this. That's next level. But before we get too deep into that, how much more efficient was his method compared to what they had before?
Great question. See, the older methods, they needed to store data on all the possible connections, which could get messy fast. Dijkstra's way. It focuses only on what matters at each step. So you get sometimes like a 90% reduction in data storage needs. Depends on how complex the graph is.
Whoa, okay, that is a game changer. Especially back then when computer memory was so limited, it's like he was Marie Kondoing algorithms, right?
Yeah.
Getting rid of all the unnecessary stuff.
Exactly. And this efficiency thing, it's super important when we get to that second problem he tackled, finding the shortest path between two specific points.
So now we're talking like proto-Google Maps, but way before GPS.
Precisely. Imagine trying to find the fastest route through a city, right? But you don't know the whole map beforehand. Dijkstra's algorithm, it figures this out step by step, only keeping track of paths that are getting you closer to where you want to go.
That's so clever. It's like exploring a maze, but instead of dead ends, you're constantly refining your route based on the new info you find.
That's a great way to put it. And again, his method was groundbreaking. Instead of calculating the shortest path to every single point, which would take forever computationally, he focuses just on the goal, constantly updating the best known route as you go.
I'm already seeing how these two algorithms, they're solving different problems, but they've got this similar DNA, that focus on efficiency, the methodical approach. It's like they were born from the same mind, which of course they were.
What's fascinating is that while they share that value of efficiency, the approaches are fundamentally different. One builds a complete network, the other's laser focused on a target. It's almost like having two specialized tools, each one perfect for a particular job. And that's where it gets interesting. How do you know which tool to use? When is it about connecting everything versus that laser focus on one destination?
Okay, you're pulling me back into the woods here. But I get it. It's not enough to know the algorithms exist. We got to know when to actually apply them.
Yeah,
I think.
exactly. Think about it this way. If you're, say, designing a network, for a small town where everybody needs internet access, minimum spanning tree, that's your go-to. You're minimizing cost, making sure everyone's linked up.
But if I'm like using my phone's GPS to
Yeah.
find the fastest route to that new ramen place across town, that's shortest path all the way.
Right.
We don't care about every street in the city, just the ones that get me to those noodles.
Spot on. And that highlights a crucial difference. Spanning tree, it's all about global optimization. Shortest total distance, shortest path. It's about reaching a specific goal, even if some parts of the journey aren't the most efficient on their own.
So it's like the difference between taking a scenic route, seeing all the sights, versus just beelining it to your destination when you're running late. And Dijkstra, back in '59, he was already laying the groundwork for both.
It's mind-boggling, isn't it? But here's something else. His work wasn't just these two problems. It was a way of thinking, a framework to tackle complexity that's had ripple effects through all of computer science.
You're talking about that breakdown into steps, the methodical approach we mentioned.
Precisely. He wasn't just handing out solutions. It was like a masterclass in algorithmic thinking. Take the minimum spanning tree algorithm. He used this elegant system of three sets, tree branches, contenders, and discards to keep track of everything.
And if I'm remembering right, This was all without the computing power we have now. He had to be extra clever with how he organized info.
Yeah. Absolutely. Imagine you're playing a strategic board game, but each move, you got to meticulously document it with pen and paper. That's the level Dijkstra was operating at.
So walk me through it. How do these three sets, how do they actually work in practice?
Picture it like you're building a bridge across a bunch of islands. Your tree branches, those are the solid connections you've already made. The contenders, those are potential bridges you could build next. And the discards, options you've ruled out. Maybe too long or going the wrong way.
So at each step, you're evaluating the contenders, picking the shortest one that connects a new island to your network, and then moving it over to that tree branch category.
Precisely. And those discarded options, they're crucial. They stop you from going in circles, reevaluating paths you already ruled out. It's this constant refinement process, making the most efficient choice at each point.
But it still blows my mind that this greedy approach, it actually leads to the absolute shortest tree. How can we be sure it's not missing some hidden, even shorter solution?
That's where the mathematical proof comes in, which, honestly, that's a whole other deep dive. But the gist is, Dijkstra showed that for this problem, the local optimum, that shortest bridge at the moment, it always helps build the global optimum, the overall shortest tree.
Okay, so no sneaky shortcuts, no hidden better solution. Greedy wins this time.
Yeah.
But I gotta admit, my brain's getting a little full here. We've covered a lot. From cable laying to island hopping, it's a lot.
You're doing great. And believe it or not, there's even more to uncover with his solution for the shortest path problem. Remember, this one's about the most efficient route between two specific points, like our ramen quest earlier.
Right, no more spanning trees. We're on a focused mission now. But I'm guessing those core principles, the efficiency, the methodical steps, those are still in play.
Absolutely. And here, Dijkstra, he introduces a slightly different system of sets. Instead of tree branches, contenders, and discards, we've got nodes. Think of them as points on our map. And they're categorized as having a known shortest path, being contender for the next step, or remaining unexplored.
Okay, I'm starting to see the parallels. Still about strategically evaluating options, choosing the best path forward. But how's this work in our ramen scenario?
Imagine starting at your current location. The nearby streets, the ones you can get to directly, those become your initial contenders. You check your map, or in Dijkstra's world, your calculated distances, and you choose the street that seems to be heading the right way.
So I'm basically doing a mini spanning tree, but just around my starting point.
You got it. And once you reach the end of that street, you update your contenders. Now it's the streets branching off from that spot. But here's the key. You're not just blindly picking the shortest street anymore. You're factoring in the distance you've already traveled.
So it's not just local efficiency. It's about the cumulative distance. Always keeping that end goal, the ramen, in mind.
Exactly. And just like with the spanning tree, you're always updating your knowledge, shifting nodes from contender to known shortest path as you go, and any paths leading away from your destination. Mentally filed away as unexplored. No need to waste brain power on those.
It's like pruning a tree as you grow it, directing the branches towards the sunlight, or in this case, the ramen. But here's what gets me. How did he formalize all this? Turn these seemingly intuitive processes into concrete algorithms?
That is the million-dollar question. And honestly, to really get his proofs takes some serious math skills. But the beauty is, you don't need to be a math whiz to appreciate how elegant, how powerful his approach is.
It's like admiring a beautiful building, right? Without knowing every detail of the architectural plans.
Exactly. And that's why these algorithms, they've lasted. They've gone beyond 1959 computing. They're fundamental tools now for problems in countless fields. But there's one more layer I think we should touch on.
Okay, my brain's pretty full of algorithmic noodles right now. But I'm ready for that last layer. What else is there in Dijkstra's world?
Well, we talked about how these algorithms work, how they're different, even how they kind of rhyme with each other structurally. But what's really wild is how far their impact goes, even outside computer science.
You're saying these 1959 ideas, they matter today, in fields beyond just making computers do fancy stuff.
Oh, absolutely. Remember the spanning tree? Like laying cable efficiently. That same idea applies to design and transportation networks, roads, railways, even airline routes. Less distance saves money, saves resources.
And it's not just physical networks, right? We were talking about social connections earlier. Could you apply these algorithms there?
You're thinking like a true deep diver. Social network analysis is huge now. And guess what? Dijkstra's shortest path. Used all the time. Figuring out how info spreads online or who the most influential people are in a group.
Whoa. So from best route to the ramen shop to understanding ideas on Twitter, it all goes back to this one guy over 60 years ago.
It really shows you the power of fundamental research, finding those core principles that explain so many different things. And what's amazing about Dijkstra, it's not just the specific algorithms, it's his whole approach to problem solving.
You keep saying that, and I gotta admit, I'm intrigued. Is it something us regular folks can learn? Or is it genius-level computer science stuff?
No, it's definitely learnable. Think about how he broke down complicated problems into smaller steps. That's useful anywhere, writing a novel, organizing a project, even planning a trip.
So it's like that saying, how do you eat an elephant? One bite at a time. But Dijkstra, he took it further. Wasn't just taking bites, he was dissecting the elephant, understanding it, before even picking up his fork.
That's perfect, and it shows another key thing, clarity of thought. His writing is so concise, his logic is perfect. No wasted effort, no unnecessary complications.
So it's not just solving the problem, it's solving it elegantly,
Yeah.
in a way that's clear, efficient, almost beautiful in its simplicity.
Precisely, and that's a lesson that goes way beyond algorithms. It's about striving for excellence in everything, finding that sweet spot between complexity and clarity.
I'm seeing why you're so into this paper. It's not just the technical stuff. It's the inspiration, the reminder that even tough problems can be tackled with a bit of ingenuity and a lot of clear thinking.
You got it. And I think that's a perfect place to wrap up. Dijkstra's work shows us that sometimes the most groundbreaking ideas, they aren't flashy. They're the quiet, elegant solutions that change how we see the world.
So next time we're stuck on a problem, right? Whether it's messy code or just fit luggage in the car, maybe we should all channel our inner Dijkstra, take a breath, break it down, and remember, the simplest answer might be the most elegant one.
And who knows? Maybe someday one of our deep dives will inspire the next Dijkstra, the person who comes up with an algorithm that changes the world.
Until then, keep exploring, keep questioning, and keep diving deep into the world of ideas. Thanks for joining us.